We will next consider how we can apply all the machinery that we've built up in terms of expansion and use of the disturbing function to analysis of n-body systems. We will start by just considering secular perturbations, and initially just secular perturbations of two bodies, and then work our way up to a general n-body secular theory. We are again considering the system where we have a central body M1, and we have much smaller bodies M2 and M3. And again, body 3's orbit will lie strictly outside of body 2's orbit, such that the orbital radius of body 3 with respect to the central body 1 is always greater than the orbital radius of body 2 with respect to body 1. We again define our ratio of semi-major axes, delta, as the osculating semi-major axis of body 2 scaled by the osculating semi-major axis of body 3. By this assumption, delta will always be less than 1. And we are still using the notation where capital D to the n represents the nth derivative in delta, and S sub I represents sine of half of the inclination of body I. So I can be, in this case, 2 or 3. We will again use our second order expansion of the disturbing function in eccentricity and inclination, and to first order in the masses, and we will only retain the secular terms, so only the terms that are independent of the mean longitudes, which leaves a very small number of terms from our infinite expansion. So for two bodies, the averaged secular direct part of the disturbing function is given by these terms only. And as before, there is no indirect part because there are no indirect terms that are not functions of the lambdas. We use this averaged RD secular term to recreate our R2 and R3 disturbing functions. Recall that they had this form. There are no indirect terms now, so we only have R2 is equal to mu3 over A3 times RD, in this case, RD average secular, and R3 is going to be mu2 over A3 times the same RD secular. Since we now have an exact knowledge of what this RD looks like, and because we have known recurrence relationships between the Laplace coefficients and their derivatives, if we further make the approximation, that is, the gravitational parameter of body 1, gm1, is approximately equal to the mean motion of body 2 squared times the semi-major axis of body 2 cubed, and equivalently approximately equal to the mean motion of body 3 squared times the semi-major axis of body 3 cubed. This is just a restatement of Kepler's second law under the assumption that the masses of body 2 and body 3 are negligible compared to the mass of body 1. Then we can write both of our disturbing functions, R2 and R3, using this one expression for R sub j. So j is again either 2 or 3, and we are defining these two new sets of coefficients, APQ and BPQ, which are given by these expressions here. The p term is always going to be given by j minus 1, that is, whichever body index we're using, minus 1. And for j equal to 2 to 3, k will be the opposite index. So when j is 2, k is 3, and the q coefficient is going to be given by k minus 1. So it might seem like kind of a pointless exercise to define all of this machinery just so that we can write both R2 and R3 as a single unified expression. But the point here is not actually compactness of notation. The point is that these APQs and BPQs represent elements of 2x2 matrices. And they are only functions of the masses and of semi-major axes, which we can consider to be approximately constant for small perturbations. So what we're going for is a linear system in these very complicated equations, which can be subjected to linear analyses. The one other thing to note is that the columns of this B matrix are not linearly independent. We are once again going to make use of a first order expansion of Lagrange's planetary equations. In this case, we have to modify them once again slightly because we are now applying them to either of the bodies instead of to just body 2 that has a massive external perturber in the form of body 3. But overall, their forms are going to be very similar. And we can write you will notice that all of these have surprisingly similar forms and that they come in pairs. The variation in the eccentricity of body J is given as -1 over the mean motion of body J times the semi-major axis of body J squared times the eccentricity of body J times the partial of the disturbing function for body J with respect to the longitude of periapsis of body J. And the variation in the longitude of periapsis for that same body has the exact same coefficient, just positive instead of negative, times the partial of the disturbing function for body J with respect to the eccentricity. And the same pattern repeats for the inclination variation and the longitude of the ascending node. They have the same coefficient, negative and positive, 1 over nj aj squared ij times the partial of the disturbing function with respect to the longitude of the ascending node for the inclination, and times the partial of the disturbing function with respect to the inclination for the variation in the longitude of the ascending node. But here's where we run into a problem. Each of these has a denominator term of eccentricity or inclination. When any of the eccentricities or inclinations in our system go to 0, these all blow up and we have singularities. So instead, we are going to define a new set of coordinates based on the components of the eccentricity and inclination vectors. Recall that the eccentricity vector for body J, in the case where the inclination of body J is approximately 0, is going to be an angle of bar pi j from whatever fiducial E1 direction we are using. We will call the projection of EJ down onto this E1 under the assumption that this angle really is var pi j d. Similarly, we are going to call the projection of this vector onto the orthogonal direction in that plane c. We can do the same thing for the inclination by defining an inclination vector that has a magnitude of the body's inclination along the line of nodes. The line of nodes for body J is exactly capital omega J from the E1 direction, and we will call the projection of this vector, whose magnitude is the inclination of body J, V, and the projection onto the orthogonal axis, U. So what this gives us is so C sub j is the eccentricity of body J times the sine of its longitude of periapsis. D sub j is the eccentricity of body J times the cosine of its longitude of periapsis. And similarly, U sub j is the inclination of body J times the sine of its longitude of the ascending node. And V sub j is the inclination times the cosine of its longitude of the ascending node. We have now removed the singularities inherent in these differential expressions. Our compacted form of the disturbing function for bodies 2 and 3 now takes this form in terms of our new quantities C, D, U, and V. You should compare this statement against this original statement and convince yourself that this is true. And the differential expressions for C, D, U, and V can be written in this compact form, where, as we've already pointed out, they each have the same coefficients. In this case, all 4 have the same coefficients because we've eliminated these denominator E sub j's and I sub j's, and they are multiplied by partials of their respective disturbing functions with respect to D and C and V and U. And this is where all of this preparatory work of setting up these matrices A and B finally pays off, because now we can write these as true linear systems. C dot 2, C dot 3 is equal to the A matrix times D2, D3. The derivative of the D's is equal to negative that same matrix times the C's. And the exact same thing is true for the U's and the V's using the B matrix. To first order, these expressions are fully decoupled and linear. And we know exactly how to solve these types of systems. We just need the eigendecompositions for spectra of A and B. We write AF is equal to F lambda, where F is the matrix of the eigenvectors of A, and lambda is the fully diagonal matrix of eigenvalues of A. And the same thing for B. BG is equal to G gamma, G being the eigenvectors of B, and gamma being the diagonal eigenvalue matrix of B. If you prefer, you can also do this in component form, in which case we use the lowercase f sub I to represent the ith eigenvector of A, and lambda sub I to represent the ith eigenvalue associated with that eigenvector. And for B, we will use G sub I and gamma sub I for eigenvector and eigenvalue respectively. The solution to this differential system is that C2 and C3 will equal the summation over all of the eigenvectors of A multiplied by the sine of lambda I times time plus alpha I, where alpha I is a phase determined by the initial conditions of the system. In a compact form, we can use this matrix notation to write C2, C3 is equal to F bar, where this bar represents normalization of the eigenvector matrix to correspond to the initial conditions, times these two sine terms in lambda 1 and lambda 2 times time plus initial phases alpha 1, alpha 2. The solution for D is exactly the same, save that these are now cosine terms in exactly the same period and phase. And exactly the same thing applies for the solutions of U and V. They are the summations of the eigenvectors multiplied by the eigenvalues acting as arguments to sine and cosine functions. And in this case, the betas, beta 1 and beta 2, are the phases that are determined by the initial conditions of the system. Collectively, this is known as the Laplace-Lagrange secular solution. Remember that we started out this whole process by using an averaged value of the disturbing function R, which means that it was independent of mean longitudes. And so what these expressions tell us is how the orbital elements will vary, but not in any way at all where the bodies were going to be in space at a particular point in time. Remember also the governing assumptions that went into this. This is a purely secular theory. There are no commensurabilities, no near resonances. A2 is always assumed to be smaller than A3, and both inclination and eccentricity are assumed to be small such that the first and second order linearizations hold. However, this exact setup can then be directly generalized to an n-body secular theory. And for explicit details on that, you can see Murray and Dermott section 7.7 or the associated reading. So how well does any of this work? Well, let's consider a specific case. We're going to treat Jupiter and Saturn from our own solar system with this secular theory. Remember that Jupiter has an orbital period of approximately 12 years, and Saturn has an orbital period of approximately 29 years, and their eccentricities are small, their mutual inclination is small, and the orbit of Jupiter always stays strictly within the orbit of Saturn. And finally, their masses, even though very, very large compared to all of the other planetary masses of the solar system, are still very small compared to the mass of the sun. So the three-body system of the sun and Jupiter and Saturn should be an ideal test case for this specific development. We are going to first numerically integrate this three-body system using a 10th, 12th order Runge-Kutta-Nystrom integrator based on Dorman 1987, and then we're going to compare that against the secular theory. In this code, we are just setting up the initial conditions based on data pulled from horizons for January 1st, 1983, which happens to match one of the examples from Murray and Dermott. We have to remove the linear drift of the center of mass of the system because the horizons data will include drift due to all of the other masses in the solar system that we are not modeling. So we just get rid of that. And then we numerically integrate and plot the results. And what we get is this. Note that the axes here are on very different scales. And so even though we are seeing a little bit of variation in terms of the z-axis component, mostly these remain well bounded within the ecliptic. The units throughout all of this are AUs and days. So we did a 100,000 year integration, recording the positions of the planets at steps of 100 years. And so you see heavy aliasing of the orbits, but over time you see that we fill in complete orbits along with some perturbations. So this is as much as we can get to the ground truth of the system. Let's compare it against the predictions of the secular solution. We set up functions for our A matrix and our B matrix, and we evaluate them for the specific mean motions and masses and semi-major axes of this particular system. The B values here are the values of the Laplace coefficients, which have been pre-computed using methods that we've previously explored. And we set up the eigendecomposition of the matrices, the initial conditions, and the normalization to match the initial conditions, which is given by the linear solution of these systems. And then we can compute the secular time histories of our C and D and U and V components and put them back together to solve for the eccentricity and the inclination. We run these and we get this solution for the inclinations. In this case, the dashed lines are the predictions of our secular theory, and the solid lines are osculating inclinations calculated from our numerical integration. And we see, once again, surprisingly good agreement, considering all of the various approximations that are taking place. Once again, we haven't quite matched the period exactly, and so we do see a shift in these over time, but we've gotten the amplitude of the oscillation and inclination almost exactly right. We do the same thing for eccentricity, and here we see that we fare more poorly. We have once again captured the amplitude of the oscillation and the eccentricities of both bodies relatively well, but we are quite off on period and phase of these oscillations. And of course, we have not accounted for any higher order effects that lead to these additional variations that we can clearly see in the osculating elements calculated from the numerical integration. The main thing that we are missing here is that Jupiter and Saturn are actually kind of near a 5-2 commensurability in periods. Remember those period numbers. 29 to 12 is near enough 5 to 2 that low order resonance actually has measurable effects on timescales that are shorter than the secular variation. And that is the primary thing that this analysis is missing. At the same time, we've neglected all of the other masses of the solar system, and Uranus and Neptune especially do have a significant effect on the overall solution. And so to get better predictive power onto what the actual solar system is doing, we do need to go to that broader n-body secular solution. However, it is essentially built up of blocks of these types of subsolutions, and we have built confidence in the predictive power of this, which means that we should have confidence in the predictive power of the more general n-body secular theory.